Assalamu alaikum, hello everyone. It's an honor to me to be with you and participate in this conference. My modest work is about the modeling and optimization of supercritical carbon dioxide Brayton cycle combined with waste heat recovery and organic Rankine cycle. Currently, energy conservation and emission reduction have drawn great attention as a result of energy shortage and environment pollution. An analysis based on the category of each study is shown on this global mapping. It seems that the most of the studies revolving around the power plant, the cost, the Brayton cycle, heat exchanger, cycle efficiency, supercritical dioxide carbon, where the color of the balls has shown the trend considering the years, and the size of each ball represent the number of studies, where the branch lines represent the integrated studies with the connected category. When coming to the power and cooling cycles, and after simple comparison, we can see that the highest performance and efficiency shown by the supercritical and transcritical cycles, of course, and that's why it's fully recommended to use it in the power industry and application of waste heat recovery and other energy systems in comparison with the common cycles used. The current work is about the combined Brayton cycle with ORC, organic Rankine cycle. It's proposed to use the waste heat exhaust gas from diesel engine. All this simulated and studied by Aspen Heises, where the Brayton cycle here compressed the dioxide carbon and then enters the regenerator. The regenerator formed after that in the state 3. It's further heated by the exhaust into HHT, of course, and here the HHT. Then it goes on into the turbine and expands to produce mechanical work. The low pressure in the state 5 flows into the regenerative part in the regeneration process, and it's cooled here, and after that we can talk about R123 is applied in the ORC here in the thickness 9, the most thickness line. So the ORC system is made up by heater, by condenser, turbine in the pump. After this, the results obtained by Aspen Heises showed in this table have shown a good agreement with the reference, and we can see that the maximum output power is required with a maximum Brayton cycle here at 20 megapascal. In this part we change the ORC working fluids and this change based on the global warming potential, ODP, and atmosphere lifetime by years. This is the four fluids with the reference and the suggestion wall. So the energetic analysis shows at 20 megapascal indicate that with the increasing of turbine inlet temperature, we have an increasing in the net specific output and thermal efficiency. And the R10 gives the highest work output. Moreover, it's clear that the R13 gives better output in the comparison with the R123, where we can find it similar here in the thermal efficiency, and this is a good sign to replace it. Secondly, what the exergy distraction analysis is illustrated here, if we compare an important exergy loss in the organic Bronchian cycle cooler and the turbine and the heater. On the other hand, we find here very slightly exergy loss, but with good optimization if we use the R13, especially the turbine and other compounds. Next, we can see, or we can, how to say, conclude all this. When we talk about this energy and about the organic fluids in comparison, in combination with the Brayton cycle, the R130, we can eliminate it because it gave us an insignificant effect on the performance if we compare it with the pollution degree, the ozone depleting, where the R10, it's highly recommended to improve the efficiency, but it's an ozone depleting. That's a negative impact. So for the best efficiency, cost, resources use, design, environment, and better sustainability, the R13 is the best choice, especially when we find that the R123 will be eliminated in 2013, and the R13 remain in the atmosphere less than 1 year. Moreover, when we use the R13, we'll have decrease in exergy distraction and in some compounds, of course, and that means a saving of cost and more economic design. Thank you for attention.